Hey guys, so in our last lesson, we talked about a little bit about Sir Isaac Newton. We talked about the first law of motion, said that an object at rest is going to remain at rest, and an object that's in motion is going to keep moving with a constant velocity unless a force acts to change its motion. But most of what we talked about in the last lesson was about finding a net force. So if we have more than one force working on an object, how do we find the sum of those forces? And you guys find the net force by adding the force vectors, right? In today's lesson, we're going to continue to work on describing the motion of an object that has forces acting on it. And today we're going to talk about the second law of motion, which is the big one, and the third law of motion. Okay, so let's go ahead and let's talk about the second and third laws of motion. Let's talk about the third law of motion first, real quick. Okay, we'll talk about the third law, and then we'll talk about the second law next. The third law of motion. Usually, you'll hear people describe the third law. They'll say, for every action, there's an equal and opposite reaction. Right? And that's the third law of motion. And by action and reaction, what they're talking about is forces. So for every force, there's an equal and opposite force. So if I were to push on my desk, then my desk is going to push back on me with the same force. You can often see this demonstrated if somebody's sitting in a chair with wheels on it. Let me demonstrate this. Hang on. So I'm sitting in a chair with wheels on it. I'm going to push on my desk and watch what happens to me. So I applied a force to the desk, right? And what happened? I accelerated in the opposite direction, right? So I applied a force to the desk, an action, and the desk applied a force to me, a reaction, which caused me to go the other way. So for every action, it's an equal and opposite reaction. So what that means is every time you apply a force to an object, there's a second force working on the thing that applied the force. So if I push on the wall pushes back on me. If I push on the desk pushes back on me. If I push on the chair, then the chair pushes back on me. If gravity pushes me down onto the ground pushes back up on me. For every action, there's an equal and opposite reaction. So they're equal, they're the same number of newtons, and they're opposite. They're in the opposite directions. And that's the third law of motion. Okay, the second law of motion, you can see right here above me. The second law of motion, this is the big one, right? This is the equation that's going to help us solve some problems, and we'll be able to predict the motion of objects using the second law of motion, right? The second law of motion says that the net force, the sum of all of the forces on an object, is equal to that object's mass times its acceleration. Now, I don't think we've done a whole lot with mass so far. Let's just mention a few things about mass real quick. Mass, lowercase m, and we're going to measure it in kilograms. If you were in chemistry last year, we usually measured mass in grams, but in physics, the standard unit is the kilogram. So if they give you something other than kilograms, you want to convert to kilograms. Probably not going to happen. But mass we'll measure in kilograms, kg. Acceleration, I know it's probably been a little bit since we've seen acceleration. Acceleration is measured in meters per second squared. And earlier, a couple of units ago when we were talking about acceleration, we didn't think about it as a vector, but now as things are two-dimensional for us, we have to understand that acceleration is a vector, right? And then of course our force, our net force, is also a vector. So if we add up all of the forces working on an object, that's equal to the object's mass times its acceleration, right? And the acceleration will be in the same direction as the net force because mass is not a vector, this is a scalar, right? So what this is telling you, this tells you there's a whole lot here. There's a lot of physics in these three terms here. But the big thing to notice here is that an object's acceleration is caused by its by the force working on it, right? If you have no force working on something, then what's going to be its acceleration? It's going to be 0. If this is 0 and that's not 0, then that has to be 0, right? So if there's no force acting on an object, the acceleration is 0. And that's the first law. If there's no force working on it, its motion won't change. Pretty cool how that comes out of there, right? So, there's a whole lot of physics right here. So this is our second law of motion. The net force is equal to the mass times the acceleration. Now let's look at how to use that a little bit. Okay, how about a little example here? It says Roberto and Laura are studying across from each other at a wide table. Laura slides a 2.2 kilogram book towards Roberto. If the net force acting on the book is 1.6 newtons to the right, what is the book's acceleration? Okay. Now, this is a really easy problem because they told us what the net force was. They told us the net force acting on the book was 1.6 newtons. They may very well tell you a whole bunch of different forces, and then you have to add them up, right? If they're all in the same direction, that's great, that's easy. If they're in opposing directions, that's great, that's easy. If they're at weird angles, then you got some vector work to do there, right? But they just told us the net force, it's 1.6 newtons. So that's awesome. They also told us the book's mass. They said it was 2.2 kilograms. And then the question asked us, it asked us to find what is the book's acceleration. Okay, so we'll just put these numbers into the equation and solve, nice and easy. So the net force is 1.6. The mass is 2.2. And the acceleration is what we're looking for here. So we'll just divide and find our answer. I got 1.6 divided by 2.2. I need two significant figures. Both of these numbers had two significant figures. So I've got 0.73. And this is acceleration, which is measured in meters per second squared. And since acceleration is a vector, we should note which direction it is. The problem said that the force was applied to the right. So for this one, we'll say that is to the right. So that pretty simple example there. Okay, so there you go, a little bit about the second and third law of motion. Hopefully that helps us to be able to describe the relationship between a force working on an object and its motion. So until next time, take it easy.